Hi, this is your video for section 5.3 about independence and the multiplication rule. The objectives in this section are 1. Identify independent events, 2. Use the multiplication rule for independent events, and 3. Identify complementary events and use the complement rule. Objective 1 is to identify independent events. So two events A and B are independent if the occurrence of one does not affect the probability of the occurrence of the other. We can also talk about several events being independent. So several events are independent if the occurrence of any of them does not affect the probabilities of the occurrence of any of the others. Now, if two events A and B are not independent, they are said to be dependent. Here's an example. Suppose you draw a card from a standard 52-card deck of cards and then roll a die. Are the events draw a heart and roll an even number dependent or independent? If you think about drawing a card and rolling a die, the results of one don't affect the other. So the results of choosing a card do not affect the results of the die toss. That means that these two events are independent. Now, suppose that you draw a card from the deck and then, without replacing the card, you draw a second card. Are the events draw a heart on the first draw and draw a heart on the second draw dependent or independent? If the first card drawn were an ace, then there would only be 3 aces left in the deck. If the first card were not an ace, then there would be 4 aces left in the deck, but only 51 cards. This means that the results of the first event do affect the probability of the second event. And again, this is because the card that's drawn the first time is not replaced in the deck. That means that for the second draw, the probabilities are changed. The deck is actually changed. So that means these two events are not independent, they are dependent. Objective 2 is use the multiplication rule for independent events. And the key word in this section is and. For two events A and B, the probability of A and B is the probability that both A and B occur. So A and B is the same as the intersection of two sets of outcomes. So we can say that the probability of A and B is the same as the probability of A intersection B. So here we're thinking about the events A and B being sets of outcomes, and the intersection of those sets is the same as saying that both A and B occur. The multiplication rule says that if A and B are independent events, then the probability of A and B is just the probability of A times the probability of B. Remember, with the addition rule, we had the probability of A or B, and we were adding here instead of multiplying. So if we have an or, then we're adding the probabilities. If we have an and, we're multiplying the probabilities. Here's an example of using the multiplication rule. Again, suppose you draw a card from a standard 52-card deck of cards and then roll a die. The events draw a heart and roll an even number are independent, as we already figured out. Find the probability of drawing a heart and rolling an even number. Again, we're going to use our multiplication rule for independent events because we already determined that these two events are independent. So we'll let event A equal draw a heart. Since there are 13 hearts in a 52-card deck, the probability of A is 13 over 52, which is equal to 1/4 or 0.25. Now let's let event B equal roll an even number. Since there are 3 even numbers in the sample space, 2, 4, and 6, the probability of B is 3 divided by 6, or 1/2, or 0.5. Since the events A and B are independent, we can use our multiplication rule. So the probability of A and B, so of both events occurring, is just the probabilities of the two multiplied together. So it's 0.25 times 0.5, which is 0.125. If we do this in fraction form, we'd have 1/4 times 1/2, which equals 1/8. Here's another example of using the multiplication rule. A manufacturer of exercise equipment knows that 10% of their products are defective. They also know that only 30% of their customers will actually use the equipment in the first year after it's purchased. If there is a 1-year warranty on the equipment, what proportion of the customers will actually make a valid warranty claim? What this is asking, really, is what's the probability that, first of all, the equipment that's bought was defective, and second, that the customer actually uses it in the first year and finds out that it's defective. So in a lot of problems, when it's asking you for a proportion, what it's really asking for is a probability. So here we'll let event A be that the equipment is defective, and we'll let event B be that the customer uses the equipment within a year. We're going to assume that these two events are independent, and for a customer to make a valid warranty claim, both events would have to occur. So again, the product would have to be defective and the customer would have to use it or try to use it within the first year. So the proportion of customers that do this is the same as the probability of both events A and B occurring. The probability of A and B is just the probabilities of the two events multiplied together. The probability of A is 10% because 10% of the products are defective. The probability of B is 30% because 30% of the customers use the equipment in the first year. So if we multiply these two together, we get a probability of 0.03. And remember our definition of unusual events. Since this is less than 0.05, we would consider this an unusual event. Now we can also look at a multiplication rule for multiple independent events. So if we have n independent events, and we're just naming them with subscripts here, then the probability of all of these events happening is just the individual probabilities multiplied together. Here's an example. Suppose that you draw a card from a standard 52 card deck of cards, record the suit, and replace the card. If this experiment is repeated 4 times, what is the probability of drawing 4 hearts? Now each draw, or each trial of the experiment of drawing a card, is an independent event because the card is replaced after each draw. That means that we have the same 52 card deck of cards each time. The probability of drawing a heart, again, since there are 13 hearts out of the 52 cards, the probability would be 13 over 52, or 1/4, or 0.25. So the probability of drawing a heart 4 times in 4 trials is the probability of heart on the first trial, heart on the second, heart on the third, and heart on the fourth. So we could calculate this by multiplying the probabilities of each one of those individual events, and each one of those has a probability of 0.25. So if we multiply all those together, we get, in decimal form, 0.0039, and I have rounded this to 4 decimal places. If we wanted to write it as a fraction, it would actually be 1 over 256. Objective 3 in this section is to identify complementary events and use the complement rule. Now we already did talk about complementary events. So remember that the complement of event A, which we write with the subscript C, includes all the outcomes in the sample space that are not outcomes in event A. And to understand this, you have to pay special attention to the wording in the problems. The wording is extremely important in determining the outcomes in an event and in determining the outcomes in the complement. So phrases like at least, more than, at most, and less than are common phrases used in probability problems. One other point here is that the complement of none is at least one. Here's an example. So consider the experiment that consists of rolling a die. Identify the outcomes in the event and the complement of the event for each of the following events. So for part A here, the event A is that the number rolled is at least 3. Now, at least 3 means that the 3 is included in the possible outcomes. So our event A would have this set of outcomes, 3, 4, 5, and 6. And our complement would be everything that was in the sample space that's not in A. So that would be 1 and 2. Now here's where the wording gets tricky, the difference between at least 3 and more than 3. More than 3 means that the 3 is not included in the possible outcomes, whereas at least 3 meant that the 3 was included. So in part B here, our event B is 4, 5, and 6 because we're not including the 3. That means that the complement of B is 1, 2, and 3 because it's everything in the sample space that was not in B. Now let's look at parts C and D. So for C, we're defining the event E as that the number rolled is at most 3. At most 3, again, means that the 3 is included in the possible outcomes. So we're taking everything up to and including 3. So our E would be the set 1, 2, 3. And the complement of E would be the set 4, 5, 6. In part D, our event F is that the number rolled is less than 3. Less than 3 would mean that the 3 is not included in the possible outcomes. Again, the difference between at most 3 and less than 3 is that at most 3, we're including the 3. Less than 3, we're not including the 3. So our event F would be the set 1, 2. And the complement of F would be 3, 4, 5, and 6. Another example of using the complement rule. Again, suppose you draw a card from a standard 52 card deck, record the suit, and replace the card. If this experiment is repeated 4 times, what is the probability that at least one of the 4 cards drawn is not a heart? Now this probability would be very complicated to calculate directly, because there would be so many different ways in which this could happen. If we think of this as an experiment in which 4 cards are drawn with replacement, meaning the card is replaced each time, on each draw we record the suit. So some possible outcomes of our experiment would be these. And this is where we're just using the first letter of the suit that came up. So one possible outcome would be that we got a heart, a club, a heart, and a club. Or we could get a heart, a club, and a diamond, or we could get a heart, a heart, a heart, and a heart. Now the sample space for this experiment would have 256 different outcomes. The event that we're interested in is that at least one of the 4 cards is not a heart. So the complement of this event would be that all 4 cards drawn are hearts. And we already found the probability of drawing 4 hearts in 4 trials. In a previous example, we found that it was 0.0039 or 1 over 256. So to get the probability of the event we're interested in, we're going to take the probability of its complement and subtract that from 1. So the probability that at least one of the 4 cards is not a heart is 1 minus 0.0039, or 0.9961. Or if we use fractions, we would say 1 minus 1 over 256, which would give us 255 over 256. And this probability was much easier to calculate this way than if we tried to think about all the different ways that we could get at least one card that wasn't a heart. Okay, section 5.4 is about counting techniques. The objectives in this section that we're going to cover are 1. Solve counting problems using the multiplication rule. 2. Solve counting problems using permutations. And 3. Solve counting problems using combinations. So objective 1 is to solve counting problems using the multiplication rule. And this is a slightly different multiplication rule than the one we talked about for probabilities. This is just a multiplication rule to count how many ways something can happen. So I call this the multiplication rule for multiple step experiments. For an experiment consisting of 2 independent events, in which the first event can occur m ways and the second event can occur n ways, the events together can occur a total of m times n ways. We can take this a little further for an experiment with more than 2 steps. So for an experiment consisting of n independent events, in which the first event can occur m sub 1 ways, the second event can occur m sub 2 ways, the third event in m sub 3 ways, and so on, the events together can occur a total of m sub 1 times m sub 2 times m sub 3, and so on, up to m sub n ways. An easier way to think about this is that to figure out the number of possible outcomes for a multiple step experiment, as long as the steps are independent, all we have to do is figure out how many ways each different step can happen and multiply all those results together. Here's an example. Suppose that you flip a coin and then roll a die. How many possible outcomes does this experiment have? This is a 2-step experiment where the events in the 2 steps are independent. So the first step, flipping a coin, can happen in 2 ways, since you can either get heads or tails. The second step of rolling a die can happen in 6 ways, because you can get any one of the 6 different faces on the die. So the experiment overall has 2 times 6, which is equal to 12 possible outcomes. Now suppose that you are designing a game as a fundraiser. Players will choose a 4-digit number. The first digit must be 1, 2, or 3. The second must be between 1 and 5 inclusive, and each of the last 2 digits can be anything between 1 and 9. So in how many different ways can players choose their numbers? This is actually a 4-step experiment because the players are choosing each of 4 digits. So we're going to look at how many ways there are to choose the 4 different digits. For the first digit, because it has to be a 1, 2, or 3, there are 3 ways to choose it. There are 5 ways to choose the second digit because it's supposed to be between 1 and 5 inclusive. And then for the third and fourth digits, those can be anything between 1 and 9, so there are 9 ways to choose each one of those. So the total number of ways that our experiment can happen is just all of those numbers multiplied together. So 3 times 5 times 9 times 9 equals 1,215 different ways for players to choose their numbers. Objective 2 in this section is to solve counting problems using permutations. Before we talk about permutations, we need to talk about factorials. So the factorial symbol, which is an exclamation point, denotes the product of decreasing positive whole numbers. For example, 4 factorial would be 4 times 3 times 2 times 1, or 24. In other words, you start with the number that's here and just decrease by 1 whole number until you get to 1, and you multiply all those results together. And in some cases we end up with 0 factorial in some of the formulas we use. So we define 0 factorial as being 1. Now permutations are arrangements of different items in order. Repetitions are not allowed, and rearrangements of the same group of items are considered to be different arrangements. So the order of selection is important. If we have n distinct objects, the number of ways to arrange r of them is n times n minus 1 times n minus 2 and so on until you get down to n minus r plus 1. Now this is a little bit hard to see with it written out this way, but if we think of it this way, we end up multiplying r numbers together. So we start with the n and we keep going down until we have r numbers written down here. That's kind of the shortcut, easy way to do this. Now the actual formula, and here's the notation, this means we have a permutation of n objects taken r at a time. The actual formula is n factorial over the quantity n minus r factorial. Now you can also do this on your calculator, and you will see a symbol on your calculator that looks just like this. Here's an example of permutations. In how many ways can 4 officers, president, vice president, secretary, and treasurer, be chosen for the executive board from a group of 30 club members? So the 30 club members are distinct, and once a member is chosen for an office, he or she cannot be chosen for another office. So there can be no repetitions in this example. And different arrangements of the same group of 4 people would create different boards, since the members would hold different offices depending on which order they were chosen in. So the order of selection is important in this case. The number of ways that the officers can be chosen is a permutation of 30 objects taken 4 at a time. And again, the things we were looking for here are that we had distinct objects, in this case our club members were all distinct, that there couldn't be any repetitions, so once we chose a member for one office, he or she couldn't be chosen again for another office, and the order of the selection was important. So those 3 things told us that this would be a permutation. So we've got a permutation of 30 objects taken 4 at a time. If we're using the formula, we would do 30 factorial over 30 minus 4 factorial. If we're using the shortcut way, we start with 30 and we write down 4 numbers. So 30, 29, 28, and 27. If we multiply those together, we get 657,720. Objective 2 is to solve counting problems using combinations. So combinations are collections of different items without regard to order. So the difference between a combination and a permutation is that permutations were arrangements of objects where the order made a difference. Combinations are just collections of items where the order doesn't make a difference. But notice in both of these repetitions are not allowed. So for combinations, if we have n distinct objects, the number of ways to select a group of r of them is n times n minus 1 and so on down to n minus r plus 1. This is, on the top here, this is the same formula that we had for permutations. But the combinations also have a denominator in this formula, which is actually r factorial. So it starts with r, and then we have r minus 1, r minus 2, and so on until we get down to 1. The actual formula for combinations looks like this. On your calculator, you'll see it as NCR, and the formula is n factorial over r factorial times n minus r quantity factorial. Here's an example. In how many ways can a team of 4 club members be chosen from a group of 30 club members? So again, here we're looking for the fact that the 30 club members are distinct. and that once a member, is chosen for the team, he or she cannot be chosen again to be on the same team, so there can be no repetitions. In this case, different arrangements of the same group of 4 members will not count as a different team. So it doesn't matter what order they were chosen in. If we choose the same 4 people, we'll have the same team. So in this case, the order of selection is not important. So the number of ways that the teams can be chosen is a combination of 30 objects taken 4 at a time. Again, what we were looking for here is first that the club members were distinct, so the 30 objects were distinct, and that there couldn't be that there couldn't be repetitions. That means that we have either a permutation or a combination. What makes it a combination is that the order that the members are selected in is not important. We're taking a combination of 30 objects chosen 4 at a time. So using our formula, it would be 30 factorial over 4 factorial times 30 minus 4 factorial. If we do it sort of the shortcut way, we have the permutation formula on the top. So we start with 30 and write down 4 numbers, and then on the bottom we have the 4 factorial. If we calculate this out, it turns out to be 164,430. Now here's an overall example of counting problems. Suppose we have 4 marbles in a bag, 1 green, 1 blue, 1 red, and 1 purple. We're going to look at 3 different questions. The first one is, in how many ways can 2 marbles be drawn from the bag if the first marble is replaced before drawing again? So we would say this is drawing with replacement, and the order of the selection is important. In this problem, since we're drawing the marbles with replacement, that means repetitions are allowed. That means that this does not qualify as a permutation or a combination, because in both of those, repetitions cannot be allowed. So we would do this one as a 2-step experiment. There are 4 choices on each draw, so that means there are 4 times 4 equals 16 ways to draw the 2 marbles. So again, we're just looking at this as a multiple step experiment. There are 2 steps, and we figure out how many ways each step can happen. The first step, we have 4 choices for the marbles, so there are 4 ways that can happen. And the same on the second step, we have 4 ways that it can happen. And we can even list the different outcomes. So these are the different outcomes that we could get from drawing 2 marbles from the 4. And if we write them all down, we can count them up and see that there are actually 16 of them. And notice here we have green, green. That means that we chose green twice in a row. So this is where it comes in that the repetitions are allowed. We have blue, blue, here we have red, red, and here we have purple, purple. The next part of this problem asks, in how many ways can 2 marbles be drawn from the bag if the first marble is not replaced before drawing again? So this would be drawing without replacement. And the order of the selection is important. Now we're drawing without replacement, which means that repetitions are not allowed. And since our marbles are different colors, that means that they are all distinct. So this would qualify as being either a permutation or a combination. And because we said the order of the selection was important, this would be a permutation. We had a total of 4 marbles, so it would be 4 objects, and we're selecting 2 of them, so it would be 4 objects taken 2 at a time. So this would be 4 factorial over 4 minus 2 factorial, or again we start with the 4 and just write down 2 numbers. So this would give us 12. There are 12 different ways to do this. And again, we can actually write down the outcomes here that would qualify. So notice that this leaves out all the ones that were in the last problem where the color was repeated. So it leaves out the green, green, the blue, blue, the red, red, and the purple, purple. And we have the other 12 left. Now, one more part of this problem. In how many ways can 2 marbles be drawn from the bag without replacement if the order of the selections is not important? Again, in this one, we're drawing the marbles without replacement, which means repetitions are not allowed. That means it could qualify as a permutation or a combination. Since we said that the order of the selections was not important, that means that this would be a combination. And again, we have a total of 4 objects to choose from, and we're choosing 2 of them, so it would be a combination of 4 objects taken 2 at a time. So this would be 4 factorial over 2 factorial times 4 minus 2 factorial, or 4 times 3 divided by 2. This would give us 6, so that means there's 6 ways to do this. And here are the outcomes. And notice there are only 6 of them because we only wrote down green, blue here. This would be the same as blue, green. So we're not paying any attention to what order the colors are in. And that's why we have 6 here instead of 12.